Welcome, everybody. This is Dynamical Roots, a journey through complex numbers and fractal geometry. So this will be a public lecture with 3 speakers, and we will alternate in a hopefully playful way and show you some hopefully interesting or cool math, or at least some pictures that you might enjoy. So let us maybe introduce ourselves. I'm Giulio. I'm an assistant professor at the University of Toronto. And with me, we have Mary and Kathryn.
Hi, I'm Kathryn Lindsey. I'm an assistant professor of mathematics at Boston College.
Hello, I'm Mary. I'm a postdoc at the University of Toronto.
Excellent. And so today we're gonna explore the topic of complex numbers and fractals and how you produce fractal geometric objects by using iteration of maps on the complex plane and things of this sort. But maybe let's start in a more playful way. Let's start with a game. So here's the game. Sometimes this is called the chaos game. So you can see there is this square, which represents part of the plane. And there are 3 red points here. And these 3 red points are labeled as 1, 2, and 3. I forgot exactly which is which, but we will find out. And there is an initial position for this game, is this central position. So the green is in central position. So how does the game work? So we start with this green point, and then we choose a number, 1, 2, or 3. And depending on the number, the next step will be that we draw the point, which is halfway between the point where we are and this red point. So for instance, we are at the center. If we push 1, so you see that the green point has moved halfway towards this point up here. So this is the point number 1. And we record also the blue one, which is the previous one. Now, if we do 2, you see that you move to the right. So the point labeled 2 is to the right. And we moved halfway. So from the original point, which was this blue point, to this new point, which is green. And then, of course, if we do 3, we can move from this point halfway towards this other point to the left, which is the point labeled number 3. And so we can repeat this procedure many times, and we're going to play this game and see what happens. So let me maybe reset. So I'm going to ask my co-hosts to tell me some numbers between 1 and 3, and I'll play this game. So Mary.
1, 2, 3, 2, 2, 3, 1.
1, 2, 3, 2, 2, 3, 1. You see this point is moving. And Kathryn?
1, 1, 1, 1, 1, 3, 2, 3, 2, 3.
1. Wow, it's going. And then?
3, 2, 3, 2, 3.
3, 2, 3, 2, 3. Very good. Let's see what else. Mary, can we keep going?
3, 2, 3, 2, 1, 2, 3.
2, 1, 2, 3. Okay, maybe let's do another one.
1, 3, 1, 2, 3.
1, 2, 3. Anybody from the audience wants to play this game with us? So you see that, yes, Mariam?
Yeah, 3, 3, 3, 5. Oh, there is no 5. Sorry, 3, 3, 3, 2, 2, 2, 1, 1, 1.
2, 2, 1, 1, 1. And Daniel says 2, 3, 1, 2, 3, 3, 2, 1. And Albert says 2, 3, 3, 1, 1, 2. And then Chapman, 1, 2, 1, 2, 3. Okay, so we have already quite a few points, but you can see immediately that maybe it's a bit not clear what will happen. We have these points that kind of spread around, and maybe, I don't know, are they just spreading around uniformly in this triangle, or I don't know, is there a pattern emerging? Of course, the mathematics is always a study of patterns, and sometimes we use computers to make it easier. So in fact, instead of having to press these buttons repeatedly, I have a different app, which is similar but different, where you can just type in sequence of numbers here. For instance, 1, 2, 2, 3, 2, 1, 1, 1, 3, 2, and so forth. Anyone else want to chime in?
2.
2. Yeah, anyways, yeah, we have this, you have a sequence of numbers, and this will exactly play the game, and you will see the response. But again, still, you don't quite see enough pattern yet. Maybe there's no pattern, I don't know, we'll see. So a way to do this is to generate a random pattern. So of course, the computer is also very good at that. So we can use this other command, random vertex sequence. And so this way, we can generate a string of 3 means 1, 2, or 3, and we can put any length. So if we do length 20, we're going to get a similar pattern to the one we have already. But we can also push it a bit further. We can do 100. And we see now, maybe there is some more complicated and more rich pattern that you can see. Well, let's see. How about 200? How about 500? How about 1,000? So at this point, I don't know, any takers? Do you see a pattern here? So mathematicians might recognize some pattern. Pascal, Sierpinski triangle, that's right. So in fact, this indeed is related to the Sierpinski triangle. So let's see, if we do 5,000, we're gonna see that you see this very, very interesting pattern. So it's not a whole triangle which is covered, but just a very somewhat small area with a lot of structure. So maybe let's finish with this 10,000. And this way, you should be able to get pretty much a very, very good approximation of this object, which is this very interesting fractal object. So this object is infinitely complicated, and part of today's lecture will be exactly to understand what are these patterns, how do they form, how can we produce such patterns, and how to parameterize the universe of all such things. So these are the kind of topics that we want to discuss. And before we do that, maybe let's end this introductory part with a kind of artistic rendition of this game that, yeah, we also coded. So here it is. Okay, so that was fun. So let's see, now we can come to the bit more scientific part of the program, where we can actually define some things in a more mathematical fashion. And in fact, the summary of today's talk will be, there will be 3 parts. So the first will be an introduction or recall for many of you about complex numbers and polynomials by Mary. And then we'll have an introduction to iterated function systems, like the one that produces the Sierpinski triangle by Kathryn. And in the end, I will come back and describe a little bit about the mathematics of trying to describe all this possible iterated function system in what's usually called the parameter space or moduli space. And well, in the end, of course, there will be even more nice pictures. But so let me give the stage to Mary now.
Sure, thanks. So let me start sharing. Okay. Okay, so as Giulio said, I will be talking about complex numbers and complex polynomials. So for, I believe, maybe half of you who have already seen complex numbers. So my part is really to bring everyone up to the same page. So let's start by talking about numbers. So what are numbers? So our familiar examples are 1, 2, so those are integers, the very first examples of numbers we can think of. And we also have fractions, so those are rational numbers like 17/7 and 2.5, which is just 5/2, right? There's also negative numbers like -100. This is a negative integer. And we also have irrational numbers like √3. And in the end, we also have transcendental numbers, which is slightly fancier. So I write pi. So those are all familiar examples of numbers. And in particular, they're real numbers. So we want to think about numbers in a more collective way. So we want to consider the collection of all the real numbers. So this is called the real line, right? So what is a real line? Well, pictorially, the real line is just a line. So here, as I drew, this is a line, straight line, and we can put all the real numbers on this line. So this is why it's called the real line. And the way I put it is I pick a point in the middle, and I claim this is the point 0. So I put the number 0 in the middle of the line. And to the right of the point 0, I have 1 and 2. So in the increasing order of the numbers, I have 1, 2, and 3.14. And so pi is slightly to the left, to the right of 3.14. So to the left of the point 0, I have -1 and -2. And in this way, I can put all the real numbers on this line. So this real line is really giving every number an address, right? So to introduce complex numbers, we need an actual new symbol, which is called I. So we should think of this new symbol I as a number such that I square equals -1. So you can also think of I as square root of -1. And we all learned in high school that we couldn't, in a real number, we couldn't take square root of a negative number. So the idea of complex numbers is to make sense of what it means to take square root of a negative number. So I is defined as the square root of -1. Right. So what is a complex number? Well, in general, a complex number is of the form x plus iy. So x is a number and y is also a real number. So a complex number has 2 parts. So the x part is just a real number, and the yi part, where y is a number. So you just write y times I. So what are some of the examples of complex numbers? Well, here I give you 4 examples. So the first example is 3. So 3 should be thought of in the formula I wrote above. So here x equals 3 and y equals 0. And whenever y in the general formula equals 0, we actually get a real number. So a real number is also a complex number. So the second example, I wrote pi times I. So pi is a real number. And in this case, x equals 0. So if we have a complex number where the x part equals 0 and y part is not 0, so you only have some number times I, so these complex numbers are called purely imaginary. And the third example is 2 plus I, so x equals 2, y equals 1, right? So this is just a complex number, and you can also make your own favorite complex number, like 1.5 plus square root of 3 times I, right? So all these are examples of complex numbers. And just like how we thought about the real numbers, we also want to think about the whole collection of complex numbers. And this is called the complex plane, right? So I drew a picture here, right? Remember, every complex number is x plus iy, right? I drew two axes. So the horizontal axis represents the part x, and the vertical axis represents the imaginary part, the y times I part. So for example, if I want to plot this complex number 2 plus I, that is to say, I want to find an address on this complex plane of this complex number 2 plus I. So this is how I do it. So this complex number 2 plus I has x part equal to 2, right? So on the x-axis, I find where 2 is, and on the y-axis, I find where 1 is. So when x equals 2, y equals 1 is the address of this complex number. So this blue dot represents this complex number 2 plus I. Okay, so let's just see another example. So now suppose I want to plot 2 plus I and 2 plus 2I all together. So for these two complex numbers, the x parts are 2, right? So for both of them, x equals 2. So the address of these two complex numbers is x equals 2. So it's like they live on the second avenue. But for the first complex number 2 plus I, the y address equals 1, right? So this complex number 2 plus I lives on the second avenue of a first street. So the second complex number 2 plus 2I, the y part equals 2, right? So this complex number lives on the second avenue and second street. So this is basically how we can think of the xy plane as the collection of complex numbers. So every complex number has an address on this complex plane. Right. So just like how we can add and multiply real numbers, so next I'm gonna tell you how to add and multiply complex numbers. So we're all very familiar with the addition of real numbers. For example, we all know how to add integers like 3 plus 5, and also we know how to add fractions like 1 over 3 plus 2.78. So what about adding complex numbers? So for example, if I have two complex numbers, 1 plus 2i and 2 plus 3i, so how do I add them up? Well, in general, you can think of 1 plus 2i and 2 plus 3i as 4 numbers, right? So just 1, 2i, 2, and 3i. And the way you add them is you just look through these 4 numbers and you group the ones without I, and you also group the ones with I. So for the without I part, you get 1 plus 2, and the rest is just 2i and 3i. So you just group 2i and 3i together. So the second bracket says 2i plus 3i. And we calculate, so 1 plus 2 is 3, and 2i plus 3i equals 5i. So this is basically how we add complex numbers. So in general, if we have two complex numbers, we can just add the x part together and then add the y part together, multiply with I, right? So this is very simple and nice. And I want to give you a pictorial explanation of adding complex numbers. So let's consider our example again. So 1 plus 2i plus 2 plus 3i, right? So we know the answer already. So the answer is 3 plus 5i. So how can we see the answer from the pictures, from the complex plane? Well, we do this. So first, we plot these two complex numbers. So 1 plus 2i. So it has address x equals 1, y equals 2, right? So here is the dot for 1 plus 2i. And the second complex number, 2 plus 3i, lives here, right? And next, we just connect these two blue dots to the origin, so to 0 and 0. So this is the point where x and y axis cross, right? So we get these two segments connecting 0, 0 to 1 plus 2i and 2 plus 3i. So what we do next is we draw a parallelogram. So we just parallel transport this red guy, so the line connecting 0 and 1 plus 2i, so that we get the third side of the parallelogram. And we can also move the line connecting 0 to 2 plus 3i up. So in the end, we can get this parallelogram by just parallel transport these two line segments. So the answer is hidden at the tip of the parallelogram. So if you draw this parallelogram carefully, you can see the tip of this parallelogram is at the address 3 plus 5i. So x equals 3 and y equals 5. So this is the answer for adding 1 plus 2i and 2 plus 3i. Right, that's very nice. And what about multiplication? And again, we're familiar with multiplying real numbers like 3 times 5. And what about we want to multiply complex numbers? So for example, again, I have two complex numbers, 1 plus 2i and 3 plus 5i. So how should I multiply them? Well, multiplying complex numbers is slightly more complicated than adding them up. So, but it shouldn't be super hard either. So what I do is I still think of 1 plus 2i and 3 plus 5i as 4 numbers. So I have 1, 2i, and 3 and 5i, right? And as we all learned already, that if you have just numbers, then there's distributive law, right? So I can multiply distributively by 3 and 5i. So let's try to do this. So I first use 3 to multiply with 1. So I get 1 times 3. And then I use 3 to multiply with this 2i. So I get 2i times 3. And then I use this 5i to distribute and multiply with 1 and 2i. So I get 1 times 5i plus 2i times 5i. So I just write these four products and try to add them up. Right, so 1 times 3 equals 3, and 2i times 3 is 6i. And 1 times 5i is 5i. And 2i times 5i is 10i squared. And we said at the very beginning, so I is a number such that I squared equals -1, right? So if I just do a little bit of calculation, so 6i plus 5i gives us 11i, and 3 minus 10 gives us -7. So in the end, we get -7 plus 11i. So this is basically how one can multiply two complex numbers. Right, so let's see one example. Again, I want to show you how multiplication works through pictures. So the first example is I want to multiply my favorite complex number 1 plus 2i by a real number, right? So remember 3 is also a complex number. So the imaginary part, the y part equals 0. So in this case, so if I want to multiply 1 plus 2i by 3, I also do this distribution, right? So I first use 3 to multiply with 1, so I get 3, and then 3 multiply with 2i, I get 6i. So basically, multiplying 3 to 1 plus 2i, I get 3 plus 6i. So now let's plot 1 plus 2i and 3 plus 6i on the complex plane, right? So the first point is here, and the second point is here. And what we can observe is that if we connect 0 to 1 plus 2i, then actually the answer, which is 3 plus 6i, also lies on this line. So this is basically saying if we multiply a real number to a complex number, the effect is basically to scale this complex number by the real number, right? So the real number here is 3. So it's pictorially, it's basically you take the point 1 plus 2i and stretch it by 3 times because we multiply by 3. So this is our first example where we can see how multiplication by a real number work. So now I want to do the other thing. I want to multiply with a purely imaginary complex number. So I still have my favorite complex number, 1 plus 2i. This time I want to multiply with I only. And according to the rule for multiplication, I distribute, right? So I use this I to multiply with 1 and I multiply with 2i. So in the end, I get -2 plus I. And again, let's plot these two complex numbers on the complex plane. So here is 1 plus 2i and -2 plus I lives here, right? And if I connect these dots to the point 0, you can see that multiplying I to 1 plus 2i is basically rotating this complex number by 90 degrees. So this is another cool fact by multiplying complex number. So this is basically a rotation. So in general, if we multiply a complex number to another complex number, so this complex number can have both x part and y part, so it's not necessarily just a real number or purely imaginary number, then this corresponds to both a scaling and a rotation. So we will see this later in our more interesting and fancier iterated function systems. Okay, so now let's talk about complex polynomials. So complex polynomials should be thought of as functions. So for functions, we should have variables, like we all know for functions of one real variable, we have f of x. But now, since we're in the domain of complex numbers, we need to have a complex variable. So this is a variable which takes values in complex numbers. So let's denote this number by z or z for Canadian audience. Okay, so here are 3 examples of polynomials. So the first example is just z plus 1. So again, we should think of this polynomial as a function, right? So the variable is z, so you can plug in different values for z, then this polynomial spits out different output, right? So the first example is really simple, z plus 1, and you can make it more complicated. So we can have 2z squared plus 3z plus 0.7i, and the third example is z cubed, and the coefficient, so the number in front of z cubed is square root of 5 times I, and you can add some extra term. So in general, a complex polynomial, which I call P of z, is of the form that you have a complex number, a sub n, times z to the power of n, plus another complex number, a sub n minus 1, times z to the power of n minus 1, plus all the way down to some complex number a1 times z, plus another complex number a0. And these AIs are called coefficients, and they are complex numbers. And this number n, so which is the largest power of z, is called the degree of polynomial. So our first example is a degree 1 polynomial, and the second example is a degree 2 polynomial, and third example is a degree 3 complex polynomial. Right, so why are polynomials interesting? Well, because we can also talk about roots of polynomial. So what is a root for a polynomial? So by definition, the root is a complex number, which I called z0 here. So a complex number z0 is a root of a polynomial p of z if you plug in this complex number z0 into your polynomial. The polynomial spits out 0. Okay, so let's just try our first example. So our first example is the degree 1 complex polynomial P of z equals z plus 1, right? And in this case, we see that -1 is a root, because if we plug in -1 into the polynomial, we get 0, right? So it's just very simple. And second example, we consider the polynomial z squared plus z minus 2. So in this case, I claim -2 and 1 are the roots, because if we plug in p of -2, so you can calculate that you get 4 minus 2 minus 2, so this equals 0. And if you plug in z equals 1, so you get 1 plus 1 minus 2, which is also 0, right? So if we know how to factor polynomials, so you can see the answer more easily. So the roots are -2 and 1. Right. So the third example, I want to illustrate that complex numbers can also be roots of a polynomial. So the polynomial in the third example we consider is z squared plus 1, right? So in this case, I claim that I and minus I are the roots, because if we plug in -I into the polynomial, so I basically get -I squared, which is I squared, plus 1, which is 0, right? And same for I. And again, we can factor, in fact, we can factor this polynomial into z plus I times z minus I. And then you can see the roots are I and minus I. Right. So as a summary, we have seen 3 examples. So the first example is a degree 1 polynomial, it has 1 root. And the second example is a degree 2 polynomial, and it has 2 roots. And the third example is again a degree 2 polynomial, and it has 2 roots. So now, a natural question you might wonder is, how many roots does a polynomial have, right? So for the examples we saw above, it seems that the number of roots is the same as the degree of the polynomial, right? So remember, the degree is the largest power of z. So for the second and third example, the largest power of z is 2. And indeed, they have 2 roots. So yeah, and from another perspective, you can see, because if you have 2 degree 2 polynomials in our examples, we can always factor. So we want to try to understand this phenomenon. Are these answers specific to our examples, or they hold a more general setup? So before I tell you the answer, I want to show you some pictures, which is basically how we plotted the roots of the examples we have seen. So the first example, z plus 1, the root is -1. And the second example, the root is -2 and 1. So they live on the real line. So the interesting thing is for the third example, where we have z squared plus 1. So the coefficient for our polynomial is 1, 0, 1, right? So the coefficient for z squared equals 1, so there's no z, so the coefficient for z is 0, and the coefficient for a constant term is 1. So this is a polynomial with real coefficients. However, it has 2 complex numbers as roots. But as you can see from the picture, these 2 complex roots are symmetric about the x-axis. So from the second and third example, you can see the roots either live on the real axis or they're symmetric about the real axis. Right, we will also see some examples which illustrate this phenomenon later. So now I will come back to the question that we asked before, right? So we want to understand how many roots does a polynomial have? So this is the fundamental theorem of algebra. So for some of you who knows what theorem means, so theorem in mathematics just means non-trivial mathematical fact. So whatever written in the theorem is true, but it's not super obvious. Okay, so let's see what the fundamental theorem of algebra is saying. So the fundamental theorem of algebra tells us that every polynomial an times z to the power of n plus all the way down to a1 times z plus a0 of degree bigger than or equal to 1 has precisely n complex roots. So this first sentence is basically confirming that what we have already seen is a general phenomenon. So for every degree n polynomial, it precisely has n complex roots. And also, if the roots are denoted by W1, W2 to all the way Wm, then we can factor our polynomial as the leading coefficients and a sub m times m bracket, where for each bracket we have z minus the roots. So this is consistent with the example we have already seen, right? And the theorem says this is true in general. It is true for any degree n polynomial. And Kathryn Lindsey will show you next a very fancy Mathematica program which illustrates this fundamental theorem of algebra.
Okay, thanks, Mary. I'm going to share my screen. So I'm sharing. Okay, so this is a document that it's in the Mathematica computing environment. And as we enter this sort of second portion of the talk, I'm actually going to keep most of my, or everything will be in this Mathematica environment. So we'll start with just a visual exploration of this fundamental theorem of algebra. So here you can see we have some coefficients, 1, -1, 2 plus I, and 3. And then here you can see, here's the polynomial that has those coefficients. So 1, and then the coefficient here is -1, and then 2 plus I. This is the way Mathematica writes I, and then a 3. And then down here we have the complex plane, and there are blue dots where the roots of this polynomial are. So Mary told us that this is a degree 3 polynomial, and so we should have 3 roots. And when we look at this picture, we do indeed see the 3 dots representing the 3 roots. There's a black circle drawn just to indicate where all the points that are distance 1 from the origin are. Let's try another one just so we can see how this works. Mary, do you want to suggest any coefficients?
Sure. So what about 2 minus 1, 1 plus I, and 4 plus I?
Okay. So there's our polynomial. And again, we have a degree 3 polynomial and 3 roots. Yeah, awesome. Should we make it more complicated? Like higher degree? How about let's add a, I don't know, -3 and then a plus pi, which Mathematica does is like that. And I think let me change that actually. I'm not sure why it didn't change the roots. Let's do a 5. There we go. Okay, so now we have a degree 4 polynomial with 4 roots shown. And as Mary was pointing out earlier, we can see that these roots occur in pairs that are symmetrical when you reflect across the horizontal axis. So let's make it a little bit higher degree. And okay, now we have a degree 7 polynomial. Indeed, we have 1, 2, 3, 4, 5, 6, 7 roots. So cool. Okay, let me just do one more. How about 1 and -1? Okay, so this is the polynomial 1 minus x. So we see that's got just a root at 1. But what if we put in some zeros in the middle? Okay, so 1 minus x to the 9th. So the roots of this will be all the numbers that when you raise them to the 9th power give you 1. And it's, okay, so cool. We can see that they're actually sort of equally spread out in this circle. And in fact, that's going to be true no matter what the degree is, if it's of this form. Let me make it slightly higher. Yeah, so now we have 13 roots spread out equally. So this is not so hard to believe because, as you told us, Mary, multiplication corresponds to doing a rotation and a scaling. And so when we do something to the 13th power, it means we have to do a multiplication and a scaling 13 times and end up with 1. So it's kind of believable that that rotation and scaling would be not scaling, but just rotation. Okay, well, cool, thank you. So now, okay, I want to use all this complex language that you've built up, Mary, to return to this question about the chaos game. So here's our chaos game. And so remember, so you pick 3 vertices and you go, depending on which vertex you pick, you go halfway from wherever you are in the direction of the corresponding vertex. So we got this cool picture. Right, okay. So let's revisit this and try to rephrase it in the language of the complex plane. So we can think of this whole plane that this is sitting in as the complex plane. And then there are 3 things that we do to points, right? Depending on which of the 3 vertices one picks. You feed it a point, the green point, and then you go halfway towards the corresponding red point. We can express each of these 3 actions as a function. So let's write f1 for the function that takes a point x, that's like the green point, and then outputs the point halfway between x and vertex 1, which I'm going to denote as v1. So, okay, we can now kind of understand how to write this as a function, a polynomial. So we want to go halfway between x and v1. So you could express this as 1/2 of x, or z, plus 1/2 of v1, whatever the coordinates of v1 are. Or in other words, you take the average of the 2 points. So that'll take x and give us the point that's the average of x and v1. And then we can write the other 2 functions that take a point x and contract halfway towards v2 or v3 in the same way. So we take x, and then we find there's the coordinates of the corresponding vertex, and we take their average to go half of the distance toward that point. Okay, so now we've rephrased our 3 actions as 3 different functions that take points in the complex plane and give you other points in the complex plane. We can now express sequences of points, as we were doing earlier, as we were getting earlier, in terms of compositions of these functions. So here's the sort of illuminating example. Say your initial point is x. Doesn't matter what it is, just some point x. And let's say we choose the vertex sequence 2, 1, 3, meaning first we go halfway toward vertex 2, then halfway toward vertex 1, and then halfway toward vertex 3. So the way we could express that now is that, so we start with x, and then to get the coordinates of the point that are halfway between x and vertex 2, we would do f2 of x. In fact, we can even see this. So so if we start with nothing, we've just got the point that is hidden, but then we go halfway towards vertex 2. And now if we go halfway towards vertex 1, that corresponds to applying the function f1 to whatever point we had. So f2 is where we got to by going halfway toward vertex 2. And then whatever that is, we apply f1 to it to get the coordinates of the point that are halfway between f2 of x and vertex 1. Then to go halfway toward vertex 3, we take whatever that point is and we apply f3 to it. And so you could go on and on. So whatever sequence of vertices we choose, we could express it in this way as doing some sequence of these functions. Okay, let's visualize what these 3 functions do. So just as a sort of nice visualization. So here's the Mona Lisa embedded in the complex plane, and we have the 3 red dots representing the 3 vertices. So right now, Mona Lisa is sort of centered around vertex 2. So let's envision what f2 does. So f2 will take any point and go contract it halfway towards the vertex 2. So we can visualize that as follows. So for example, if you pick the point that say Mona Lisa's nose, where is it going to go when you apply the map f2? It will go to where her nose is now, and you can keep applying it. And the other vertices, the same thing will happen. So I think this is vertex 1. Wherever you are in the complex plane, if we apply F1, you'll shrink halfway towards that point, and so on. And then finally, if you're, you can shrink halfway toward vertex 3. So this is showing the effect on the entire complex plane of applying the maps F1, F2, or F3. Okay. So just formalizing what we've been saying, if we have any quote unquote word in the alphabet, 1, 2, 3. So what I mean by that is just some sequence of numbers, 1, 2, that are 1s, 2s, and 3s. And then any point X, we can express the sequence of points as whatever you take, whatever the first vertex is, so maybe W1 is like 3. What your point that you would get would be F3 of X. And then you do whatever the second one is. And so you apply F, and then whatever that second vertex is to what you had, and so on. Okay, so formally, we say that these 3 functions, F1, F2, and F3, define an iterated function system. Okay. Now, okay, so great. But what if we started with a different initial point, right? So when we played it before, we saw like the Vivaldi and the game we played at the beginning, we started with our point at 0, 0. But what if we start somewhere else? So what this little demonstration here shows is the effect of starting at various initial points. So if you can see, there's this little crosshair target symbol. That's where we start. So actually we could make this really, here, let's do just 1. So we'll contract halfway towards vertex 1 from wherever we start. So we start at the crosshairs, and then when we apply 1, we go halfway from that, wherever we started, towards vertex 1. So you can see if I change our starting point, the point that we get changes. Okay. So clearly different starting points will give us different sequences. Let's just make this a little longer, 2, 2, 3, 1, 2. Okay, so as we choose different starting points, so different X's, we would get different patterns. So it is interesting they move around, but what if I plot more points? Let me just do a random vertex sequence. So that was with just, so we've got 3 vertices, and let's do, say, 10 points, a sequence of 10 vertices. Okay, so you can see choosing different starting points, it does make the points move around. But what if I now do 100? So it kind of looks like we're still getting different patterns, but they're kind of stabilizing. It's kind of settling down. Okay, what if I do a sequence of 500? Now you can see it's even more stable. It's depending, sort of the overall picture is depending less and less on where you start. So there might be, it does change, but it's getting, okay, how about 1,000? Okay, now this picture is changing even less. You can see it does change a little bit, but 10,000, you can barely see the picture change at all. So I think we could keep doing this. And I think what this shows, or at least makes believable, is that as your sequence, your randomly chosen sequence of vertices gets longer and longer, it matters less and less what your initial point is. And in fact, that is true. If you were to take sort of an arbitrarily long sequence, this picture would be sort of arbitrarily stable. Okay, so starting with different initial points doesn't really change this limiting picture that we get. And now another question we can ask is, so we've got this picture, this shape that was earlier identified as the Sierpinski triangle. So what happens if we apply the 3 generating maps to this set, this shape. So, earlier we did it with Mona Lisa. We saw what happened when we applied the 3 generators. What if we apply the 3 generators to this set? Well, so here, this set is shown in sort of this bluish purple color. And then in yellow, what you see is what you get when you apply, so there's a 3, so that means F3 going halfway towards the 3rd vertex, starting at every single point in this blue-purple shape. So it's the image of the whole shape when we contract it, when we apply F3. What if we apply F2 to the whole blue-purple shape? Yes. Okay. So F2 takes the whole shape and sends it to just this upper part that's shown in green. And what if we take the whole purple shape and we apply F1? Well, I think you can guess. Yeah, we get the bottom right corner. So, okay, so what are we seeing? We're seeing that this whole shape, this sort of limiting invariant shape, is made up of 3 pieces. And those 3 pieces, what they are is what you get when you apply each of the 3 generating maps to the whole shape. So here we see how the 3 pieces make up the whole shape. Okay, so here I've just sort of written what we just saw down. So let T be the symbol that denotes this limiting shape, the triangle shape. So we saw that T can be written as the union of 3 pieces, and those 3 pieces are F1 of T, F2 of T, and F3 of T. So a fact is that this particular set is the only set that has this property. Now I got to put in some qualifiers. Non-empty, because if you have the empty set is equal to the empty set, and then the whole complex plane also has this property. So I've got to put compact, but in fact, this triangle shape, the Sierpinski triangle, is the only non-empty compact set that has this property, that it is equal to itself when you take its image, the union of its image under the 3 generators. This set is called the attractor or limit set for this iterated function system. And the second point here just illustrates what we saw earlier, that your initial starting point doesn't matter. So that is, if you take a long enough sequence of vertices, you get closer and closer to a picture where it doesn't matter what point you start with. Okay. Furthermore, we saw that this process of starting anywhere and then just applying a really long sequence of the generating maps gives you a way to draw this set, the limit set. Okay. So the cool thing is there's nothing really special about this set of 3 functions, F1, F2, and F3. I mean, it's a little special, but we could have used really any functions. So instead of using those 3 functions, you could just imagine any list of functions, which I'm now going to call G1, G2, all the way up to Gn. There has to be finitely many of them, but just some list of functions that take points in the complex plane, or if you prefer, you can think of the real plane, and output other points in this plane. But the one little caveat is that when you think about these things, you usually want each of your functions to be a contraction, meaning that if you have any 2 points and you hit both of them with your function, any of the g's, that it decreases the distance between them. So instead of F1, F2, F3, you could just have any list of functions, and collectively, such a list of functions are called generators for an IFS. And so essentially, this whole discussion will hold for any collection of maps like this. So here's a theorem. This was proved in 1981 by Hutchinson. And what it says is that if we've got an iterated function system generated by any set of contraction mappings, then there's this attractor or limit set exists. That is, there's a unique non-empty compact set that has this property that it's equal. It can be written as n pieces, one piece for each generating map, and the pieces are what that map does to the whole shape. So this is exactly like saying the way this picture was the union of the three pieces corresponding to the three generators, exactly the same thing happens in general. So let's play with this a little bit. So the first thing we can observe is, hey, let's just like tweak our system just a little bit. Instead of having 3 vertices, let's have, say, 5 vertices. So here we've got a chaos game with 5 vertices. And it's going to work exactly the same way. So you start with some point and you label your 5 vertices, 1, 2, 3, 4, 5. And then you randomly, well, you pick some sequence of vertices and you go halfway towards the corresponding vertices over and over. Okay, so here with 10 points, we can't see so much. Let's do 100 points, 1,000 points, 10,000 points. Okay, and a kind of a picture is starting to emerge. So this set, oh, I got overly greedy. I asked for 20,000 points, it's thinking. So this set will be made up of 5 smaller pieces. And it's the unique set that has the property that the whole set is made up of these 5 smaller pieces that have the structure that each one is the image of the whole set under one of the generating maps. You know, we could do it with, okay. I mean, okay, so let me just 200. You know, what if we do 4 generators? Oh, I have to do chaos game of 4. 4 generators. So 4 generators, and let's do 100 points. Okay, so 10,000 points. It looks like the whole square is filling in. Okay, one more. Let's do 7 vertices, and then a random sequence of 7 vertices. Oh, sorry, I have to evaluate. And it's thinking. Stop that. All right, maybe we'll just move on. I think you can imagine what the one with 7 will look like. Okay, so that was like the most basic thing we could do to get a different iterated function system. But what if instead of going half of the distance to the vertex, we go a different fraction of the distance to the vertex? So in this version of the chaos game, instead of going halfway between wherever you are and the corresponding vertex, you go 3/4 of the distance to the corresponding vertex. 3 and 100. Okay, let's make it 1,000. Okay, and what if we go 9/10 of the way? And I got to type random vertex sequence again.
Kathryn, there's a question from the audience.
Oh, I'm sorry. Yes, thank you. What is it?
Is a certain fern going to make an appearance?
Oh, a certain fern is going to make an appearance. And actually, maybe that's a great lead-in for what's coming next. So what I want to do is I want to show, so far we've been talking about iterated function systems that are just contractions. But as Mary was talking about, multiplication by complex numbers can also do rotations. So we should look at some iterated function systems that involve both shrinking or both scaling and rotation. And so we're going to do that next. But before we do that, and it's going to be a really cool picture, because time is going by and people might need to like take a break, we're going to take a 5-minute break. So that's the lead in to the next thing. So it is now 8 minutes past the hour. At 13 minutes past the hour, we're going to resume and we will see we'll see some cool iterated function systems. Okay. So as promised, we want to see some more iterated function systems. So let's do, I have one more example and then we'll switch to the third part of the lecture. So here's a different iterated function system. And this one is going to have two generators. And so rather than writing down the formulas for what these maps are, these functions, I'm showing it pictorially. So one generator will be the map that takes the red square. The red square is kind of hidden behind the blue and the green square, but you can imagine, you can see where the red square is. It'll take the red square to the green square. So it'll take the red square, it'll just kind of rotate it 45 degrees counterclockwise and then move it a little bit. And then the other generator doesn't involve any rotation. It just takes the red square, it shrinks it, and then it moves it a little bit. So now we're starting to put in rotation. Okay, so let's see what the limit set is. We can do this by playing this chaos game. So here, there's two generators, and I've labeled these two generating maps as generator 1 and generator 2. So I can do the same game, you know, if I can do any sequence 1, 2, 1, 1, 1, 2, 1, you know, and I can see what the sequence of points that we get is. And, you know, okay, you're like, yeah, I get to the point. Oh, I need one more. Okay, but so let's see now, random vertex. I'm still calling it random vertex sequence, even though they're not vertices anymore. They're just 1s and 2s telling you which of the two generating maps to apply. So actually, I guess I just need to say 2. And okay, let's make sure this works. We'll take a sequence of 10 of them. Yep, okay. Here's the magic, 100 of them, 1,000 of them, 10,000 of them. Okay, so I think this is so darn cool. So out of those really simple functions, we get this incredibly complex structure arising. And so I titled this little app Fern Chaos Game because it looks like a fern, obviously. And it's kind of nice that we see that actually there are lots of things in nature that have this sort of self-similar structure. Okay, so with that, I will now turn it back over to Giulio, who's going to show us more iterated function systems. Okay.
Thank you, Kathryn. Thanks everybody who is still around. Unfortunately, yeah, this lecture is getting a little long, but hopefully we'll make up for it with it being nice and entertaining and interesting, hopefully. So yes, so now we're getting into the real sort of really nice part, which is actually very close to contemporary math research. In fact, Kathryn and I are working on papers related precisely to this, and there's lots of recent research which is related to this. And so I'm going to start with considering, again, this iterated function systems that Kathryn described, and we're going to use this complex interpretation. So we start with lambda. Lambda would be a complex number, and we'll have to have modulus less than 1 for reasons that you will see immediately. So they have to have constructions. And there will be just of this form, where you have only two maps, which we call F plus and F minus. And they're given by Z goes to lambda Z plus 1 and Z goes to lambda Z minus 1. So it's the same category of maps, basically, just a slightly specific setting. And so again, how does this work? Well, we take a random sequence of plus and minuses, for instance, I don't know, plus minus, and so forth. And you apply these maps in corresponding order, as we discussed. So, and remember, exactly as Kathryn said, there's this limit set, which can be thought of as you take these maps, you apply them, you take a starting point and you apply them in all possible ways, in infinitely many ways, in all possible ways. You take the closure of it and you get this complex set, which could be interesting. And at this point, we're going to use this notation k lambda, So the limit set will be denoted by K. Usually in mathematics, we denote compact sets with K. So this is K lambda. And it has this property again that there are two sub copies of it. So there's K lambda, if you apply the map F plus, you get a sub copy of it. And if you apply the map F minus, you get another sub copy. So we will see very shortly pictures. So this is just to recall the setting. And also an interesting observation that comes out of applying this map over and over is that if you have a point in this limit set, can be actually represented in the following form. So basically you can choose these epsilon k's are coefficients which could be +1 or -1, depending on which sequence of maps you're choosing. And it turns out that you can represent each point as, well, not quite as a polynomial, but as an infinite polynomial. So for mathematicians, this is called the power series. So basically, you take this coefficients plus or minus ones, and you multiply each of them by a power of lambda. And fortunately, since the modulus of lambda is less than 1, this converges to some number. And so you have a point. And so basically, there is an address. So the way you represent these points on this limit set is like this. So I give you an infinite sequence, epsilon1, epsilon2, and so forth. And this gives you the address. So it tells you how to get to that point using this formula. And also note that it will be important soon that, in fact, points might have more than one address. So if I give you a value of x, there could be different sequences, epsilon k's, that actually represent the same point. And that will be, in fact, very important. So let me show you what kind of examples I'm looking at, again, using mathematical simulations. So, okay, so let's start with this one. So remember that this system, at each time, you start with a point and it produces 2 points, and then it produces 4 points and so forth. So in this particular one that I've chosen, you start with this point, central point. You apply this map, you get 2 points. Then you're going to get 4 points, then 8 points, 16 points, then maybe this overlap with 32 points and so forth. And what shape do you get this time? Well, if you keep going, you see that you have this pattern, and eventually you get a shape of this form, which, for reasons that you can kind of guess, it's a traditional called the twin dragon. So you see that there's this region, and this boundary of this region has this very complicated shape. It's very wiggly. And in fact, it's a curve that, if you really know a bit more of mathematics, you will see that this curve has dimension which is bigger than 1, which is very strange. So let's try again. So you start with 1, 2, 4, and so forth. And you're going to get this twin dragon curve. So this is a type of thing that we want. So another thing that we could do is we have the systems that depend on the value of lambda. And so I can choose this value of lambda. So remember that the main topic of this final section is to describe the parameter space, as mathematicians would say. So basically, you want to describe the universe of all such systems. And so the way this works, you can pick a point. Remember, you have to pick a complex number of modulus less than 1. So in this red circle, this gray dot represents the choice of such element. So, and for any such choice, this red picture shows the limit set. So for instance, if I pick a choice on the real line like this, you see that the limit set is this kind of dust. It's not clear how many points there are, but it has this dusty feeling. And if you pick another point, you see that on the real axis, you always see this kind of dust behavior. But if you pick a point which is not on the real axis, you have a much richer possibility. So if you pick it along the imaginary axis, you have this rotation by 4 symmetry, which again is very closely related to what Kathryn was saying, that multiplication by I is rotation by 90 degrees. So you would see that there are very strange, these are very sort of kind of regular behaviors, but even weirder things can happen. For instance, if you go here, you will see that you will find again the twin dragon. Okay, you can't maybe see it precisely because you just see an approximation, but it turns out that you see that this becomes the dragon. So let me go down a little bit again, because otherwise it's too slow. But so, okay, so in general, you would see that you get this dust-like picture. And then at some point, if you go around, you see this dance of this limit sets. This limit sets becomes more complicated. And they, at some point, for instance, they come together. For instance, you see that you have such a picture like this. For instance, this is, in this picture, you see that it's no longer a dust-like set. It's more like just a big chunk. Still has this very fractal nature to it. And so you see that for each choice of lambda, so for each point in the circle, you can find some strange set. So for instance, and this sets again could be sort of made of infinitely many pieces like this, or they could be just sort of coming together and make just a big unique piece. So for instance, if you wait a second, you will see that you still have, they can still have holes in it. It's very complicated what could happen. It's a very rich family of systems. And so we are interested now in two different properties of this system. So one is whether this has infinitely many pieces or not. So for instance, this case would be a case where the set is so-called disconnected. Means that, for instance, you can draw a line through the plane which separates the set in two parts. So for instance, if you draw, I don't know, the y-axis, you're gonna see that half of the set will be on the left and half on the right, and nothing precisely in the middle. But in other cases, like in the dragon case and similar cases, you have a set which is usually called connected set, meaning that it is made of only one piece. Okay, let's see. Right, so in this case, you cannot really cut the set in two parts unless you break it. If you draw a line, a line which has if you draw, say, the y-axis, it has some bit on the left-hand side and some bit on the right-hand side, but it's it basically has to cut through the set. So this space is called connected, because you can't really separate it into. So this is precisely what we want to discuss. And so we want to discuss whether these limit sets are connected or not. And that's indeed topic of a very serious modern research. So in particular, we can say, as I said, that the subset of the plane is disconnected if it can be separated in two parts, say by a curve, and otherwise it's connected. So for instance, this set, you see that you can separate it in two parts, say left and right. So this is disconnected. And this one, the dragon, is connected because, well, if you try to draw a line to separate it in two parts, well, this line will intersect the set. You cannot really separate it neatly in two parts without cutting it.
It seems you didn't screen share.
Sorry, you can't screen share?
You didn't screen share your.
I didn't screen share. Oh, I'm sorry. Okay, sorry. Okay, so as I said, so this is an example of a disconnected set, can be cut in three parts. And this is an example of a connected set, which cannot be cut in two parts. And so what we are discussing now is what's usually called the connectedness locus, meaning the set of lambdas. So lambda is some number which can change. For every lambda, you have a different system. So lambda is called the parameter usually. And so the question is, for which lambda is this set connected? And precisely this is the definition of the connectedness locus. It's the set of parameters for which this limit set is connected. And in fact, there's an easy characterization, very nice, is that this limit set is connected if and only if, so this condition is equivalent to having that the two parts that the limit set is made of intersect each other. So let's go back to the dragon picture. You see that the dragon picture is connected. It only has one piece. And one way to tell this is because you see, if you apply the map F plus to the whole dragon, you see the left part, this red dragon. And if you apply F minus to the whole dragon, you're gonna get the blue sub-dragon, so to speak. And these dragons intersect each other. You see, there's a point in the middle, for instance, which sort of belongs to the boundary of both dragons. So these two pieces collide together. And this indeed is equivalent to the limit set being connected, because if it's disconnected, basically there is no collision between these two parts. And so now I hope this is clear enough, and I will actually give you proof of something, which is maybe a bit more mathematically challenging, but still kind of basic, is that you can use this characterization to characterize this connectedness locus, and then we will show pictures of this. So maybe even if you don't completely get the proof, you can enjoy at least the pictures that come next. But so the idea is this. So if the set is connected, it means that there is a point in the middle, for instance, that lies on both subdragons, and meaning that he has two addresses. There's two ways to get to it. You can come from the red part and you can come from the blue part. And so basically you can write this point P as this combination of epsilon k lambda k for some epsilon, so this is one address, and for some other address epsilon tilde. And then you just subtract these two things. So if you subtract term by term, you get that the sum of epsilon k minus epsilon tilde k times lambda k, this one has to be 0. And what are the possibilities for this difference? Well, you can see that you see epsilon k is plus or minus 1, and epsilon k tilde is also plus or minus 1. So if you have plus plus, you have plus 2. You have plus 1 minus 1, you have 0, and you have minus 1 minus 1, you have minus 2. So these are the only possibilities for these coefficients. And if you divide by 2, you see that you're going to get coefficients plus 1, 0, or minus 1. And so this is an interesting theorem. This is already non-trivial mathematical theorem proved by Thierry Bouch, I think, in the early 80s, which is the following. You can characterize the set of parameters lambda for which this limit set is connected in the following way, that these lambdas satisfy also an equation of this type, basically that there's a polynomial or an infinite polynomial, so to speak, with coefficients 0, plus 1, or minus 1, such that lambda is a root of those. So you see that you have a problem which describes infinitely many dynamical systems, and now you want to study the space of parameters, so the space of lambda for which certain property holds. And in fact, in this case, it's relatively simple to characterize, but still not so simple because you can see the pictures of this. So what if you plot the set of such lambdas? So here's what happens. So here's the connectedness locus for this family. So basically, we're plotting in this picture, in fact, we're just taking all polynomials with coefficients 0, plus 1, or minus 1. And in this case, up to length degree at most 14. And we draw all the roots. So you have a lot of roots because there's exponentially many such polynomials. So you have a lot of roots and you plot them in the complex plane. And so you get this bagel-like picture. And also the shading of this picture is related to how many roots there are. So you're plotting a lot of points. And if there's more points, it's the whiter, it's brighter, and it's darker where there's fewer points. So here you see that you capture the richness of all these possible limit sets together. So you have fern-like behavior here, for instance. You have maybe dragon-like behavior, like I don't know here, and you have all sorts of other types of behavior here. You have also you see also some fractal pictures. Here you have also, it seems like there's like several layers of dragons on top of each other, but this is not clear. There's not really any layering here. It's just that you plot so many points together and you come up with this fractal structure. And there's also these holes, which are very interesting because, in fact, some holes are kind of round, but these round holes eventually, in fact, if you iterate for longer, they will be filled in. But there's also like more complicated fractal holes, like here, for instance, I guess, where they really exist and they're not going to get filled in. And so this set is already extremely rich, and it's been the subject of many papers in mathematics. And in fact, not a lot is known. I mean, we know it's connected. We know it has some holes, maybe infinitely many, but really there are so many questions about this set still. And also, let's see, maybe there's a question. Are these related to Mandelbrot and Giulio setting? We'll get to that soon. So also, there's another property we can look at, which is the following, which is the property of, second. Okay, and so there's another thing we can look at is that the set of parameters for which the limit set is connected, rather than being connected, we can ask whether it contains 0 or not. This is also a nice property, which is kind of similar to the previous one. And in fact, at some point, we could see that the twin dragon, for instance, contains 0, but there are other cases where there's kind of a central hole, and even if the whole thing is connected, still there's this hole. And it turns out that you can prove similar conditions. So in fact, the set of parameters for which the limit set contains 0 is the set of lambda, which satisfies such an equation. So it's a polynomial or power series, again, in lambda, and the coefficients now are just +1 or -1. So you don't have 0 anymore. So you see that this immediately becomes a subset because the condition is more strict. So it's harder to verify. And this also is very closely related to the picture that we have on the poster for this conference, because this, in fact, is a graphical rendition of this. And you see immediately the richness that you see. Again, you have ferns, you have dragon-like behavior here. You have this other behavior that we've also seen here. We have all these layers, and again, here you can draw some sort of density plot by taking how many roots there are. And so also, you can play with the graphics if you want to. Just like you can make it black and white. So in this case, the blacker means there's more points. And okay, you can make it blue and so forth. So you see that there is this very, again, natural looking feeling of this picture. And however, this is precisely just generated by this complex iterations and this iterated function system. So this is kind of beautiful. Another thing you could do is you could overlay the two loci. So basically, the green shape is the first one that we were looking at, this one. So this is the connectedness locus. And the blue one is the set of where the limit set contains 0. And if you overlay, you see that they're not the same. And in fact, we've seen that one is given by coefficients 0, 1, or -1, the gray one. So it should be bigger than the blue one, which is only given by coefficients +or -1. And in fact, that's precisely what we see here. So you see that you have this richness in this parameter space. Now, someone asked about whether this is related to the Mandelbrot set or not. And in fact, well, not quite, but we're going to end with this nonlinear family. By the way, this is also another picture closely related to this, which is basically we're studying the inside of this bagel, and we constructed with Kathryn some function that you can be used to study the inside of this bagel. And in fact, the level sets, resemble a spider, and so that's why I called it the spider. But this is for further research. So this is really open problems. I mean, this is really something that has not been fully explored yet. So there's still lots of interest. So, but let's go to the connection with a more, maybe even more classical complex dynamical system, so the quadratic family. So if you look at the usual quadratic polynomial family, it's usually given like this. So you have a polynomial of degree 2, which is z maps to z squared plus c. So c is a number, which is a parameter, meaning that we fix this number and we consider the dynamical system defined by that function. And then we change the number and we consider another dynamical system. So for instance, if c equals 0, you get the map z goes to z squared. If c equals 1, we get the map z goes to z squared plus 1. If c equals I, you're going to get z goes to z squared plus I. So the variable is z and c is a parameter. And there's a classical way to define Giulio sets, but in the spirit of this lecture, I think there's even easier or even more similar one to this one that we've done for iterated function systems. So you can consider a nonlinear iterated function system, which is the following. You use the square root, the complex square root. So you take a point z, and you do z minus c, and you take the square root. And in the complex numbers, every number has 2 square roots, so you consider both of them. And in terms of dynamics, this is like you take the preimages of this map. So you have a map from the complex plane to itself, and every point has 2 preimages. And then if you have 2 preimages, you take further preimages. Every 2 points have 4 preimages and 8 preimages and so forth. And the Giulio set can be described as the limit set of this iterated function system. And we will see immediately pictures about what happens in this setting. And in the end, the most famous Mandelbrot set, which again is really one of the most fascinating objects in mathematics, is precisely related to this connectedness locus, is the connectedness locus for Giulio sets. So basically here what you do is you change your parameter c, and you plot different Giulio sets, and you look at which Giulio sets are connected and which of them are not. And if the Giulio set is connected, your point C is in the Mandelbrot set. But yeah, this is not the usual definition, but it's equivalent, and it's more in the spirit of today's lecture. Okay, so let me go to the graphical part. So let me show you what happens when you do this nonlinear iterated function system. So, okay, this is the linear one that is really beautiful already. And in fact, we can also put the backdrop of the bagel, and we're gonna see what exactly I already showed you before, maybe. Yeah, so this is the backdrop of the bagel. And you see that if I pick a point which is not in the bagel, then the limit set does not contain 0. So like in this cases. On the other hand, if I pick a point in the bagel, the limit set is, well, now it's a bit hard to see. You have to maybe iterate a few more, but you will see that it contains 0, you see. And if you're here, even closer to the unit disk, it's even more complicated. But if you're outside, if you click outside in the central region, you see a very nice counter set. So you see a set which is totally disconnected. So this is the linear one. How about the nonlinear one? Well, in the nonlinear one, you can do exactly the same thing. So for instance, here, you remember the dragon simulation? We did the same in a nonlinear case. So you pick a point, you take the 2 preimages, and then 4 preimages, and so forth. And you see that this accumulates to this strangely looking set. And this is precisely, okay, not a very good graphical rendition, but you can start seeing this pattern of this Giulio set, which appears. And you can also do it with, say, a complex number. So this is when C is a real number. If it's a complex number, for instance, if it's I, so you got to consider z squared plus I, you can see a picture of a Giulio set, which is the following. You see that you have this kind of electric feature to it. It's called a dendrite usually. Okay, so this is all nice. And so let me finish with exploring a little bit about the relation between Giulio sets and Mandelbrot sets. So here is precisely what is usually experimented when you want to study the relationship between Giulio set and the Mandelbrot set. So on the left-hand side, you have a Mandelbrot set, and you have a set of parameters. So basically, you have a complex plane, and if you click at a point on the complex plane, you see this yellow cross. On the right, you could consider the corresponding Giulio set. So in fact, if I pick a point at the center, you're going to see that the Giulio, not the center, but close to the center, the Giulio set is some sort of bubble. And I can move around, and you see this bubble changes, becomes maybe more round or less round, but it still kind of looks like a bubble. More fractal, maybe. But then the more complicated things happen. So for instance, if you go here, you no longer see a bubble. You see a picture with these lobes. In this case, this Giulio set is called the rabbit. You can kind of guess that, I don't know, Duadi was very imaginative and he saw a rabbit in here. On the other hand, if you go to the other side, to the real side, like this way, you go to the left, and you're gonna see this example is usually called the basilica. Again, Duadi imagined the Basilica of San Marco, like, which would reflect itself in the water. So it's kind of very poetic image. And you can keep going, and you see that, and as you change your parameter, you're gonna see extremely rich geometry in this Giulio sets. And if you go outside of the black region, you see, well, it's not so easy to see, but this limit set that you have becomes disconnected. Okay, this is not so easy to see in this picture. You see this kind of yellow dust, but yeah. And of course, the Giulio set has the Mandelbrot set has extremely rich geometry. For instance, here, you can see that there's a smaller copy of itself. So you see another small Mandelbrot set inside. And you can see that immediately you can keep going, zooming in, and this picture keeps happening. So you have another small Mandelbrot set, which is further inside, and so forth. This is kind of remarkable, ain't it? Baby broths, that's right. So yeah, there are these baby Mandelbrot sets that, of course, are very, very popular among also science popularizers, but indeed, extremely professional mathematicians are working on this, and there are still great open conjectures about the geometry of the set. So it's not just because of the pictures. Of course, today, I think we have a lot, we've already covered a lot of territory, so we possibly don't have more time to discuss further properties of this set and all this nice dynamical properties that there are, but definitely there are a lot of them. And so I think I might leave you, since we are towards the end of the lecture, I think I might leave you with this interesting zoom image of one of this baby Mandelbrot. So thank you for your attention.